Hello, everyone. Welcome back. So today we're talking about testing claims about two dependent samples and specifically about samples we consider to be matched pairs. So our goals then, understand the difference between independent and dependent samples, what we mean by that, understand how to write hypotheses when testing claims about such matched pairs or dependent samples, and also when we test those claims using the p-value method, all those other methods can be used. So what do we mean when we say dependent and independent samples? So if you see my previous videos on testing claims about two proportions, two means, those are considered to be independent samples, basically that weren't related to each other in any meaningful way. So we say that samples are independent if the sample values of one population aren't related or somehow naturally paired or matched with samples from another population. Then dependent then would be the opposite of that, if they are paired or matched in some way to each other. So for example, it'd be samples from the same subject, from the same person, samples like before-after data, or something like that. As dependence, it says, does not require a cause and effect relationship, but basically they're just potentially they're matched or dependent on each other in such a way that we can't consider them to be independent. But basically it's important for the ways the tests themselves are constructed. So let's talk about testing claims and about dependent samples. So actually, I'll just read this. It says, let D be the difference between two values of any matched pair. Remember, difference means subtract. So we're going to subtract for each, take the sets of data, put them together, and essentially where these matched values, we're going to subtract one matched value from the other. It doesn't really matter which one we subtract from the other, but then we create these differences, and then the mu D is the mean of the population of these all these differences of these matched pairs, not the means of each individual data set, but the means of these differences, average of all these differences. Okay. For a sample of matched pairs, D bar then is the mean of the differences of the sample of matched pairs, and SD is the standard deviation then of these differences of the samples of the sample of matched pairs. And basically, we're going to create the differences D in matched pair data. We subtract in a consistent manner, such as like if we have before and after data, subtract before from after, or the other way around. And we'll see some examples which will make this more clear. So our hypotheses are going to be very similar to what we've seen before. Okay, so the null hypothesis is there's no difference in the matched pair data. They're basically the same. And so basically there's no difference between them. Then this mean, although there may be differences in individuals, this mean then of these differences should be zero if there's no real difference in the populations. So essentially all the times one is greater than individuals when greater than the other will essentially kind of cancel out. And then the mean will be essentially be zero, that basically indicate there's no difference between these matched samples. But alternate hypotheses will be one of the other three usual options, either that the difference is not equal to zero, that there is some difference, although not specifying a direction, or that these differences are greater than zero, indicating that one, essentially one sample is greater than the other, like maybe before is greater than the after, or the other way around, or they're less than that, maybe the before data is less than the mean of the before data is less than the mean of the after data, for example. But similar setup, okay? Our requirements here, just for means, are similar to what we've done before. So we assume the sample proportions are still from random samples, but the two samples are dependent. They're matched pairs. And then once again, you want your sample data to be larger than 30, although these tests are usually pretty good for values when that's not the case. And the ones we do actually will not be the case, but we're going to assume that they're from populations that are close enough to being normal or close enough to being bell-shaped distributions that we can use them. In the StatCrunch, we're going to do a very similar place we've gone before. So we're going to stat, then t-stats, and actually a pair to do this. So let's take a look at some examples, a couple examples. And also, once again, I didn't show you the t-statistics. These can be kind of complicated, potentially. So let's take a look over here on the right. It says, a popular theory is that the presidential candidates have an advantage if they're taller than their main opponents. Listed below are the heights in centimeters of presidents along with the heights of their main opponents. So this table I've taken from a textbook. So this column gives the heights of the presidents, and then in each year, this was the height of that person's opponent. And once again, this is why they're called matched pairs, because they're not really, these samples are not independent of each other, okay? So it makes no sense for trying to test this to compare just the average of this column versus the average of this column. We're trying to actually test year by year in a sense. So what we're going to do then is use the sample data here, with a 0.05 significance level, test the claim that the population of the heights of the presidents, the main opponents, the differences have a mean greater than zero. Okay. So let's consider this to be kind of a essentially population for the presidents, the opponents. Our alpha once again is 0.05, and our mu, our sample data, and what we're essentially doing is for each, and StatCrunch will do this for us, but for each pair is going to be the president's height minus the opponent's height. Now, it's okay to do it the other way as well, but just to make sure we're consistent. So the presidential height minus the opponent's height. So essentially we're doing for each paired sample, this minus this minus this, and so forth. And that gives us then the value of these differences. And then the question is, are these differences, if these differences have a mean greater than 0, that would mean that essentially presidents tend to be taller than their opponents. Okay, so let's look at our hypotheses. So our null hypothesis, let's go back and take a look again at our hypotheses, is going to be that the mean value of these differences is equal to 0. Basically, there's no difference between the heights of presidents and the height of their opponents. And then the alternate then is going to be that this mean difference is going to be greater than 0. Okay, that's the claim, that basically we're assuming that presidents have an advantage. So we want to do it as the presidential height minus the opponent height. And then write these means, the mean of these differences is greater than 0, means that potentially on average, essentially, that the president, if we subtract these, presidential height minus opponent height for each individual year, then those differences are going to be positive. The mean difference will be positive, and that means that typically presidents will be taller than their opponents. And see if there's enough. So the question is, there enough evidence to support that claim? All right, so once again, let's go to StatCrunch. Now, what I've already done is I already put the data into StatCrunch. So you'll see that. Yeah, so here's our data. So what we're doing then is, once again, StatCrunch will do this for us, is subtracting this value, this minus this value for these two columns. And then we'll determine also then the test statistics and everything. So go to Stat, and once again, T-stats, and finally go to Paired. Okay, so it gives us the choice of two columns. So select column 1, and it gives us presidential height, and sample 2, the opponent height. Okay, and it's doing it as 1 minus 2, mu1 minus mu2. And so we're going to use the same thing here. So mu d, the mean of the differences is 0. That's our null hypothesis always. All to this case was that those differences would be, the mean of those differences would be positive, be greater than 0. Okay, so double check, make sure everything's correct. And then usually compute, and then let's copy this data into our Word document, and then we'll take a look at what we have. And once again, we can save this for later if we want. Go back and look at it again. Okay, so from StatCrunch, so let's see what we have. Okay, and what this gives us then, it calculates the mean. So the mean of those differences is positive. Okay, it's 3.6. Now, we don't know yet if that means it's significant or not, but that's what the value is. Okay, and then so we need, once again, is our t-stat, t-statistic, and our p-value. So the t-stat is 2 places 1.30, and the p-value is 0.1246. Once again, we want to compare the p-value to, write that better, compare the p-value then to the critical or the significance level. So I'm actually kind of limited space here. So let's see if I can kind of put this all together here. So once again, what we want to do is compare And actually, let me do a really small graph of what's going on. So once again, here would be like our normal distribution. Here is the mean of those differences being 0. And we're saying it's greater than. So over here is our p-value. And the question is that smaller than alpha? So compare the alpha and the p-value. And the p-value is 0.1246, and our alpha was 0.05. And so obviously, if we compare that, then the p-value is larger. And of course, once again, what that means is we don't reject HO. So we do not reject the null hypothesis in this case because the p-value is too large. And if I can squeeze this in, what this means is there's not enough evidence to support the claim that the mean of differences in height there's not enough room to squeeze everything in. Essentially, that the mean and differences of heights between the president and their opponents is greater than 0. Once again, at 0.05 level. I'll just say squeeze it in level. Okay, so let's read that again. So there's not enough evidence, so you did not reject, to support the claim that the mean differences in heights of the presidents versus their opponents is greater than 0 at this 0.05 significance level. Write that a bit better. Okay, so there's not enough evidence to say that presidents tend to have a large, or presidents tend to be taller. There's not enough evidence to support the claim that presidents tend to be taller than their opponents. Doesn't mean this isn't true. Just means, once again, with this data we have, there's not enough evidence to support that. Of course, in both cases, if you notice, those were small data sets. So perhaps we take in larger data sets, something, possibly we might have more information. It might be different, but we just don't know that. And then, so get one more example. And this one says, listed below are the body temperatures for 7 different subjects measured at 2 different times in the day. Use a 0.05 significance level to test the claim that there is no difference between body temperatures measured at 8 a.m. and 12 p.m. So once again, for 7 people, they measured their body temperatures at 8 a.m. and 12 p.m. So once again, these are, this is, once again, this idea of being paired data, because they're paired by person, okay? Like the presidential value is kind of paired essentially by year, by election. This is paired by person, essentially the before and after. Now, our alpha is 0.05, and we're going to do this, and it doesn't matter which way we do it, because the question here is, for each pair, is there a difference? We're not asking direction. So here I'll just say, so for each pair, we're going to do 8 a.m. minus 12 p.m. And once again, that's a choice. It doesn't really matter as long as you understand the direction you're using. Okay, so once again, let's look at our hypotheses. So our null hypothesis is that these differences we make, we subtract all these temperatures for each person, is that there's differences would be 0. That means there's no mean difference, no average difference between them. And then our null or alternate hypothesis, H1 or HA, is the claim is there's no difference. Okay, it was actually the same as the claim as the null. So then our alternate, so it doesn't mention direction greater or less than, is going to be that there it's not equal to 0, that there is some difference. And we'll see if there's enough evidence to support that claim. So let's go to StatCrunch again. And already have loaded that data as well. Okay, so you can see here are those data values for 8 a.m. and 12 p.m. once again, go to stat, go to t-stats. And also we're going to t-stats because we don't know anything about the population standard deviations. Go to paired, and then once again, select the column. So we're going to do, we said we'd do 8 a.m. minus 12 p.m. So column 1, make sure it's 8, and then just be consistent. Column 12, make sure it's 12. That's what we chose. And then here, our null hypothesis is that, of course, mu is equal to 0. And then this one is that mu is not equal to 0, simply that they're not equal. And then make sure everything's correct, hit compute, and same thing. So once again, let's copy this data into our Word document so we can use it. And we'll come back right here and plug it in. And let's see what we have. Okay, so we just need our t-statistic. All right, this time we know, so this time our mean is negative. So this mean differences is negative. So that, at least for the mean, this samples kind of suggest that it might be, if it's negative, that might mean that the 12 p.m. temperatures, at least for the sample, on average 12 p.m. temperatures are larger than 8 a.m. temperatures. But that may or not be true, may not be able to claim that of the population. That's our goal, see if we can, there's enough evidence to do that. Okay, so our t-stat is equal to, in this case, it's negative 7.50, which is quite far from the mean. And as you expect then for that, then our p-value is going to be 0.0003. Okay, so usual thing once again, so compare the p-value. Alpha, because once again, if we draw a picture of this, a basic picture, and this time this is a two-tailed test because here's our mean difference is equal to 0. So we're looking at both. Okay, so this is our p-value divided by 2. And we'll see if the p-value is less or greater than alpha. And it's clearly less, as we can see. So the p-value is 0.0003. And the t-statistic is negative, sorry, the t-stat. The significance level is 0.05. Clearly the p-value is less, so once again, that means we can reject the null hypothesis. Okay, let's look back at our claim then and see how to state that. So the claim was that there's no difference between body temperatures at 8 a.m. and 12 p.m. Okay, now, so then there's enough evidence to reject that claim. Enough evidence to reject the claim that the mean difference, I'll just abbreviate difference in body temperatures temp from 8 a.m. to 12 p.m. is 0. Okay, even let me say this, because that's true, but yeah, there's enough evidence. This is when we say reject the claim that the mean difference in body temperature at 8 a.m. and 12 p.m. is 0. And so we can simply say there appears to be some difference in body temperature. Once again, this is at 0.05 significance level. So there does appear to be some difference in body temperatures based on this, but since our test was simply the testing claimed they were equal, all we can say from this test is that there's enough evidence that they're not equal. But we don't know that if it's true, and also we don't know a direction. The mean kind of suggests being negative, kind of suggests that 12, since we did it as 8 a.m. minus 12 p.m., kind of suggests that the 12 p.m. values are higher, but that's not the test we did. You could also do a separate test for that and say that maybe that mu of d is less than 0 and see what happens. But the test we did, all we can say is that there's enough evidence to reject the claim that there's no difference. There does appear to be some difference statistically, but we don't know the direction based on this particular test. Okay, so what we learned today then is kind of the difference between specifically independent, dependent samples. So we're looking here at samples that are dependent in some way. And the reason that's important is because the way the algebra and calculus and mathematics go into making these tests, that's actually an important distinction. So you have to make sure you use the correct tests if you have data that are dependent on each other. In this case, they're matched in some way, matched pairs. So we want to understand what it means to be matched pairs, for example, like before after values, like in the second example, or either matched by the same person in the temperature example, or matched by election, matched by year in the presidential example. And then we learned that basically we create then differences, essentially a sample of differences where we subtract individually each value one from the other, like a before after, or in this case, the president minus the opponent. We create that column of values, and then we find the mean and standard deviation of that set of data, and then we create our hypotheses based on that. So null hypothesis is that mean of those differences is zero, meaning there's no difference in, for example, the before and after, the matched pairs one to the other, before and after, for example, or that we say that there is some difference, and then possibly give a direction either that if it's positive, then one is larger, positive, or if it's greater than or less than another, equal to zero. That means that one, if we think about before and after, like in the second example, that's the best, easiest way to think of it. Then mu being zero, mu of d being zero means there's no difference statistically. As we found in this example, we have mu of d equals zero for our alternate hypothesis. We found that that was statistically significant. There was a difference. Okay. Or also, if we said the way we did it here is that 8 a.m. minus 12 p.m. If we done it as alternate as mu d being greater than zero, that would be claiming that 8 a.m. temperatures were higher than 12 p.m. temperatures. Or if we claimed it is less than zero, that'd be claiming 8 a.m. temperatures were less than 12 p.m. temperatures. And so we learned that how to use StatCrunch then to determine those values. And then to either reject and use the same p-value method, which is very similar to what we've done in other examples, use the p-value method to then reject or not reject the null hypothesis, then summarize the test. Thank you. Have a good day.